Hello! In this video, we are going to prove the following theorem. Let a be a real number between 0 and 1. Then for all positive integers n, a to the power of n lies between 0 and 1. Now let's remind ourselves of our definition of non-negative integer exponents. Let a be any real number. Then for each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. So a to the power of 0 is going to be equal to 1, and a to the power of n plus 1 will be equal to a to the power of n times a, for every non-negative integer n. Now, from here it follows for every real number a to the power of 1 is equal to a. Because if we take a to the power of 1, we can substitute 1 for 0 plus 1. So now we're in a position to apply the recursive part of the definition, right? Taking n to be 0, a to the power of 0 plus 1 is just a to the power of 0 times a. And a to the power of 0 is just 1, so this is just 1 times a, which is equal to a. So we see a to the power of 1 is equal to a. So now let's get into proving this theorem. Now we are going to prove this statement by induction. So let's start with the base case. In the base case, we are trying to show that a to the power of 1 lies between 0 and 1. Well, we know a to the power of 1 is equal to a. So, since a lies between 0 and 1, we can substitute the a with a to the power of 1. So a to the power of 1 lies between 0 and 1. And that's it. This completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n, and we assume that this inequality is true. The whole goal of the induction step is to show that a to the power of n plus 1 lies between 0 and 1. Well, by the recursive part of our definition, we know that a to the power of n plus 1 is equal to a to the power of n times a. And since a to the power of 1 is greater than 0, and a is greater than 0, well, product of positive real numbers is positive. So it follows that a to the power of n times a is greater than 0. Since a to the power of n plus 1 is equal to a to the power of n times a, this is saying that a to the power of n plus 1 is greater than 0. So now all we have to do is show that a to the power of n plus 1 is less than 1. Well, we know that a to the power of n is less than 1. Since a is positive, if we multiply a on both sides of the right-hand inequality, well then the sign of the inequality remains the same. We're going to be left with a to the power of n times a is less than 1 times a. And 1 times a is equal to a, so we get a to the power of n times a is less than a. But a to the power of n times a is equal to a to the power of n plus 1. So this is saying that a to the power of n plus 1 is less than a. But since a to the power of n plus 1 is less than a, and a is less than 1, that tells us a to the power of n plus 1 is less than 1. And so 0 is less than a to the power of n plus 1, which is less than 1. And so we're done. This completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So by mathematical induction, we have proven for all positive integers n, a to the power of n lies between 0 and 1. And so this completes the proof. And so yeah, that's pretty much it for this video.